So in this video I'll be looking at ExamCraft 2017 Leaving Cert Higher Level Maths Paper 1 Question 4, and it's a complex numbers question. The complex numbers Z1, Z2, Z3, Z4 and Z5 are shown below. Z2 is equal to 2 times Z3. Okay, so wherever Z2 is, Z3 is going to be on the same line as it. Just what does minus 2 do to it? Well, if I were to just multiply it by 2, I would be increasing its modulus, whereas if I'm multiplying by minus 2, I'm making it on the other side of the origin. So the origin here, what's interesting about these three complex numbers here is that they are all on the same line. They are collinear. That's also interesting about Z2, Z1 and Z3. Z1, wherever it is 3 times further out than Z3. So if this is Z3, what is 3 times further out than that? Would be Z1. And remember what we said about Z2. Wherever Z3 is, if I go 2 times further out, it would have been here, 2 times further out on the same line, but back through the origin, back around. Okay, so this down here is going to be Z2, which leads us on then to thinking about Z4 and Z5. Well, Z4, wherever Z3 is, we are going to multiply it by I. So Z3 is here. Remember, what does multiplying by I do? Multiplying by I rotates it 90 degrees anti-clockwise, and we can see that. That's a 90-degree angle formed right there. So that means this one right here is Z4. And process of elimination, we know this is going to be Z5, but I'll explain why it's Z5. So Z5 is Z3 plus Z4. So Z3, imagine if we were to draw an arrow up to Z3 from the origin. And Z4, if we were to draw Z4 plus Z4. What if I was to add those two arrows together? So Z3 plus Z4. Whoa, slow down. Z3 plus Z4. I could drag this. This is how I add vectors together. It's called top the tail. The top of the red arrow must go to the tail of the purple arrow. And look, it gets to Z5 up there. So that's how I know Z3 plus Z4 is equal to Z5. Okay. Question 2, or part B, sorry, question 4 part B is written out incorrectly. It should be investigate if the modulus of Z1 over the modulus of Z2 is equal to the modulus of Z1 over Z2. So it's investigating, does the order of the modulus matter? Okay, well, what is the modulus? We know the modulus of A plus BI is equal to is square root A squared plus B squared. So the modulus of Z1 is equal to square root 2 squared plus minus 5 squared. The modulus of Z2 is equal to minus 1 squared plus minus 3 squared. And what do both those equal to? 4 plus 25, square root of 29 for the top one. 1 squared is 1, 3 squared is 9, so square root of 10. Okay, so I have Z1, the modulus of Z1 and the modulus of Z2. What I really want to deal with here now is this bit. First deal with Z1 over Z2. That's 2 minus 5i all over minus 1 minus 3i. How do I divide a complex number by a complex number? I multiply top and bottom by the conjugate of the bottom. 2 by minus 1 is minus 2. 2 by 3i is plus 6i. Minus 5i by 1 is plus 5i. Minus by plus is minus. 5 by 3 is 15. I by I is I squared. How do you multiply a complex number by its conjugate? You use A squared plus B squared, so it's minus 1 squared plus minus 3 squared. Minus 2 here, just gonna worry about this. That's minus 15 I squared, which would, and I squared is minus 1, so that's plus 15. So it's minus 2 plus 15, which is 13, plus 11i all over 10. Okay. And then that simplifies even further. 13 over 10 plus 11 over 10i. So that's z1 divided by z2. But what's the modulus of z1 divided by z2? It's going to be the square root of a squared, which is 13 over 10 squared, plus b squared, which is 11 over 10 squared. Put that whole thing into your calculator. You get the square root of 290 over 10. And we know z1 over z2, modulus of top and bottom, equals to z1 over, dropped my calculator. What do we have? This is the square root of 29 over the square root of 10, equaling to the square root of 290 over 10. Do they equal to each other? Yeah, they actually do. Imagine if you're multiplying top and bottom of this bit by root 10 over root 10. So root 10 over root 10. What would you get on the bottom line? Root 10, and the reason I'm allowed to multiply by root 10 over root 10 is because root 10 over root 10 is 1. So imagine what you get. Root 10 by root 10 is 10. And then root 10 by root 29 is root 290. Or you could just type both of them into your calculator. Type both left and right into your calculator. And you'll decimalize it, and you'll find that both decimals would be the same. So we're going to say true. Okay. And the last question then. A fairly rare question. It's an application of De Moivre's theorem. If you want, you could look at the last video, or not the last video. It's in the complex numbers playlist on this channel. It's complex numbers number 9, applications of De Moivre's theorem. It's a bit of a long video. It is about half an hour, but it covers this whole topic really well. There's only sort of 4 questions that can come up that exist like this, and it talks it through this area of complex numbers thoroughly. But anyways, quickly going through the question. So use De Moivre's theorem to prove the identity cos 3 theta is equal to 4 cos cubed theta minus 3 cos theta. What you start off with is you start with cos theta plus I sine theta to the power of 3, and that power of 3 is dependent on this number there. If it was the number 4, you would start off with the number 4. If it was the number 5, you would start off with the power being 5. We multiply it out using De Moivre's theorem, and we multiply it out not using De Moivre's theorem. So you can see that I would have gone cos theta plus I sine theta by cos theta plus I sine theta by cos theta plus I sine theta. And I multiplied out 2 of the cos theta plus I sine thetas to get us this. Okay. Then I continue to multiply out. Now in the red there, I've sort of on the left hand side here said that we're only interested in cos theta. So remember, these two must equal to each other. I'm multiplying it out using De Moivre, and then not using De Moivre. But they should really still be the same thing. Just because I'm using a theorem to multiply it out, or I'm multiplying it out long ways, it should really be the same thing. So note, at this point, I only care about the things that won't have an I, because look, the cos doesn't have an I over here. If the question was talking about sine 3 theta, I would be taking this bit and then taking over here only the bits that would have an I, because the sine 3 theta has an I over here. So I just take my time and go, well, cos theta by cos squared theta would be cos cubed theta, and it won't have an I. Cos theta by 2i sine theta cos squared theta, well, that would give me an I, so I don't multiply that out. Cos theta by minus sine squared theta is minus sine squared cos theta. And then I by 2i is 2i squared, but 2i squared is minus 2. Sine theta by sine theta is sine squared theta, and I still have the cos here from it. Okay, so this section is coming from the blue bit over there, and this bit, those arrows, explains this bit right here. Now I look at it and go, well, is there any joining up that can be done? Yeah, there absolutely is. Sine squared theta cos theta, sine squared theta cos theta, minus 2 sine squared theta cos theta gives us the minus 3 sine squared theta cos theta. I'm missing a theta there, but my pen is not small enough right now. Zoom in, use a smaller pen. There you go. I factorized out sine squared theta, and I used the trick that comes up an awful lot. You see the red bit, so the red bit here, I've factorized out the sine squared theta plus cos squared theta is equal to 1 from page 13 of the log table. Sine squared theta is equal to 1 minus cos squared theta. That's that red, that bit of substitution there. And I continue to multiply out then, and I get to what I was asked to be proved, and that's the question done. It's kind of interesting that this is a mock question, because it's a pretty long one, as you can tell, pretty difficult as well. If it was going to come up in the Leaving Cert, there would be a very, very, it's not going to be well answered, but I think it's a brilliant question. So I would put a bit of effort into it. It's not that hard once you can wrap your head around it, and hopefully you found the video somewhat useful. Suppose if it was a Leaving Cert question, I think this would probably be worth more than 5 marks. I think this would probably be 10 marks, and I think it'd probably be badly answered, that this would probably end up being worth 5 marks the first time it came up, but if it came up a year or two after coming up before, then it would be worth 15 marks. Similar to Damara's theorem, when it was first asked to be proved, it was only worth 5 marks, I would say, because it was poorly answered, and then it was asked 2 years later and was worth 15 marks. So if it comes up the first time, probably not a lot of marks. Comes up second time, probably a hell of a lot of marks.